Yeah, so I'll be blagging a bit more on this technology than other stuff, how I move these slides. So those of you will know I'm named after Neil Armstrong. Tomorrow, this guy here, Kennedy, does a really great speech. Actually, I listened to it. Before I go on stage, I listen to it because just the way he nails it is just amazing. If you haven't listened to it, go do so. Sadly, we now have Boris Johnson doing speeches, how politics have failed us. Anyway, so you know who BT is. I've done these slides before. We spend lots of money on research. And I talked about this before, where we can have a whole program on different parts of the network. And one of the other areas that none of you, and I think our sponsors later on, are really focused in this area. Security remains one of our kind of unfixed challenges. And one of the worries we have is that if I just skip on to that slide, one of the worries we have is a lot of our security that we have in the network today and in applications is based on public key kind of exchange, SSL type technology that we've kind of been using forever. And whilst that served us well, there is a lot of theory in quantum compute that would effectively make that technology pretty worthless from the point of view of securing anything, both in two dimensions. One, knowing whether you've been in kind of attacked, and two, actually really being able to secure for the future. So if you believe what some of the computer science say, and Google, I think, are a real big investor in this space, quantum computing platforms are not far away. There's a load of theory on this that's really worth having a high-level understanding of it. In case, you know, because if this stuff materializes, it's going to change how we think about building networks altogether. Then the other challenge we face is ensuring that, you know, more and more data is secure. So that we've seen some high-profile hacks recently. Some are really basic. Anyone affected by BA's issue this week? I've got 2 credit cards that were stopped because I used them. It's kind of infuriating. And then with GDPR, that glorious regulation, you know, knowing where your data is and how you're storing it, where you're putting it, and who has access to it. You know, the direction of travel is really pushing us to think very differently. I kind of used to have a belief that, well, we're here just to carry the packets, and it's someone else's problem to secure it. And as long as we can carry the packets, life is good. I'm kind of changing that view because it's kind of like an N factor situation where, because there's so many issues, that if we don't tackle them, it becomes really hard to carry the packets. So we've got a program on security, and in particular on what we call quantum-based security. So today, as I said earlier, we all kind of know this. We encrypt and we decrypt, and you know, life is good. We do a whole load of symmetric cryptography, and you know. That works for the most part, but increasingly, as we really want to use this technology to the maximum, we need to transmit keys securely. So one of the challenges we face when we're rolling out more secure encrypted networks is, you know, the technology is great, except you've got to be able to figure out how do you get the key to the site in a way that's genuinely secure. People will say, oh, well, I can install it on the box before it goes there. So then you need to know the installer and your whole supply chain from whoever made that box to how it gets on-prem is secure, and that's actually really difficult. In fact, having tried to do it, it's impossible, and actually in my mind, it's hugely more complex than before. So, you know, even in today's world where I say, well, I'm just going to encrypt all my traffic, if you don't have a way of generating the root key that genuinely is secure, then eventually someone will figure out a way to tackle that. And you know, you have platforms today that are, you know, tamper-proof, etc. You can buy that from many vendors, but they still rely upon someone with a USB stick sticking that original key in or generating it on the platform, which is even more scary because most CPUs and how they generate keys have a lot of exploits. Which leads us on to the next thing. Who here has tapped a fibre? How hard was it? Really easy, right? So imagine you hired a van, you painted a logo on the side of it, you drove to a street, somewhere in the street, you lifted the fibre out, happened to be outside the London Stock Exchange or something like that. You put a fibre tap in, you sit there all night, and probably if you're ever in London at night, it's pretty much where most Ethernet stuff gets pulled through ducts and stuff from BT and all the other operators. You can sit there all night, and probably no one will question what you're doing. And of course, we're all legitimately installing new services, but it wouldn't be that difficult for someone to sit there for probably. I actually almost feel like I want to test this. Like, how long could I sit, next to a fibre termination point, pull it out, and how long could I just sit there hoovering up all data? I think probably days before someone really stops. So if you do see a van sitting around for more than a day, even if it's an OpenReach van, knock on them and just make sure that they look like telco engineers rather than evil villains. Or maybe they're the same. Before someone else says it, Will. So really easy to do that, and there's no way. There's no way of detecting that. And then if you put that with what comes out of quantum compute, where you'd be able to, even if it was encrypted, you'd be able to decrypt it. We reckon this is less than 10 years away. Then you really have a big challenge, because even if you try to secure it, you've got quantum cryptography, which, okay, that's kind of a van-sized platform, but you could have a big enough van to have that in it, and you probably get away with it, or you just have a 4G link back to it, and you've probably got enough bandwidth on 4G now to make a decent job of a 1 gig link. So you've got two challenges. One, encryption's under attack, and two, it's relatively easy to pick up and tap somewhere. And I've used an extreme example of in the street, but you walk around some data centers, particularly the low-end shared ones, and it wouldn't be that difficult to do that, I believe. I'll go back to why will computers be able to crack the encryption. So the key issue with encryption algorithms is they actually rely on being easy in one part. And then if you've got a way, and actually if you spend enough time on it, even without quantum compute, you could eventually break a key. So then you say, oh, just double the size of the key. But then when you introduce quantum compute, and I'll refer you to kind of Shor's algorithm. Actually, Wikipedia have got a pretty decent write-up of it. I really encourage you to read that to understand how this would work. But in effect, it would be able to find the keys really quickly, like in the blink of an eye, quick, and that's very scary. And this isn't tomorrow, but it's. I believe it's near enough in the future that we need to start thinking about it. So what would we do about it? So we came up with this notion, and we didn't come up with it. We observed some guys in Switzerland who were talking about how you could use the physical components of a network to manage and add security. So if you imagine in an optical network, you have a laser that shines light down it, and in that you've got a number of photons that are all at different frequencies, different power levels, different phase, different polarization. And actually, for the most part, all of those things are now predictable in a network. Even with technology that's 10 years old, you can kind of predict what will come out of a laser and then what you will see at the other end. The beauty of this solution is, if someone taps it, it changes the physical properties of the light. So immediately, it's slightly dimmer. Probably nothing you'd notice with your eye, and please don't look at lasers or anything with a laser on it. But you could easily detect that the power has changed. Probably the phase and polarization has changed, and if you're really silly, the position will change. And that's detectable. It's detectable at the other end. It's also it's actually also potentially detectable at the source if you think of how you might see some refraction coming back down the line. The other advantage of this is you're actually using the properties of the transmission to create the key. So the key is constantly changing. So even if someone grabs the key, it's probably got a half-life of milliseconds. And you can use that. You could start with some fairly crude, just random number generators, and change the key so often with the light it wouldn't matter. But then actually you could then use the quantum capability in quantum compute to generate a much kind of more complex key that would be harder to break. The simple fact being is I've got two things here. One, the key never lives long enough that I have to worry about it anymore. And two, if someone does snoop what's going on, I can detect it. And that's the essence of what we call quantum key distribution. And this just explains. This kind of just goes into the detail of that. It's fairly straightforward. If you imagine you've got Alice and Bob, and then you've got this evil person called Eve, you can detect that she could pick up the key, decode the key, and then decrypt anything. But then, if you try and extract the key using a mirror of the photons, well, actually the photons have changed, and therefore the key's changed. So it's really hard to extract the key, even if you tap, because you're using the physical properties of light in an optical fiber or in any other sort of technology. So you might think you've got the key, you apply it, and actually it won't decrypt the traffic that you've got. I'll talk a little bit about polarization behavior, because this really even gives you another kind of way of detecting this. So if you imagine a single light beam, it's polarized vertically. Again, we know that's how it's done, and we let the light through. If it's polarized, if the alignment changes, we never let it through. And then all of a sudden, if we see anything in between that, we know something very weird's happening. Maybe someone's listening in, maybe something else, maybe another problem on the network that allows us to go and look at that. So that gives you a kind of understanding of, even at the simplest level of polarization, you can really easily see that something weird has started to happen, and this is very, very easily detectable. It's more of the same. You can see the polarization in both states, and then one state will work, the other state won't. Polarization, we looked at that as a way of doing this, but actually it's quite it's probably one of the harder ways to do this solution. So we kind of parked that for a little bit and looked at phase and pulse. And if you look at here, this kind of talks the same thing, which is what's the state of the light as you send it in versus what's the state as it comes out. And again, probability says if you're seeing these things, then you've probably got something bad going on. So Bob compares his random state with the sender for every single photon. Which just the scale of that makes it really hard to crack. Eve doesn't know what state to measure, and if she tries to guess, she changes the polarization. And then that's detectable at both ends. You'd detect that, and you'd know that someone was trying to do something, or that perhaps you had something going on. I'll skip this slide because it's more of the same. So we built so there's been a lot of experimentation in this space, and we decided to try and build this using real commercial hardware. So working with ADVA, and then we're also working with a couple of other players in this space, predominantly Toshiba, to try and build this solution so that we could actually use, is this deployable in the real network? And actually we're able to make this work, and if someone interjected into any part of the fibre, we could detect it almost immediately. And also it was really hard for them, even if we gave them the key at one point in time, it was really hard for them to do anything with it. And then so we got that working with 10 gig, and then recently we got it working with 100 gig. And actually this was a couple of years ago, but it was still very much lab based. So whilst it was real kit, we were kind of using rolled fibre in our labs. But again, we were able to work it with 100 gig, which actually we thought would be a challenge because all the kind of modulation issues with 100 gig waves. And then we did a real proper demo of 100 gig encryption with QKD links. We used high-speed encryption systems, and really we were able to show a real proper platform that was deployable into the network. We're using standard stuff, Gemalto encryption stuff. Some of you will be familiar with that. Really easy, really simple for us to get it up and running, and it works very well. Again, working with Adva on the network side, who were fantastic. But the challenge is, one challenge we have is with that you're kind of limited to 100 kilometers, because if you need to do regeneration, then you kind of lose the photons. So you end up going back to a world where we're trying to make optical paths as long as possible, so we don't need to do any regeneration or any come back to electrical to go back to optical. So we came up with another idea, which was to use kind of satellites, and there's a couple of different ways of doing this. One is you kind of build to the satellite your secure part, and then you can use in a number of technologies, but the one that I think has got real potential is free optics. So you're actually going to use the laser from the ground station to the satellite. Again, it'll have light properties that you can encrypt the key on. It's got light properties that will change. As long as you don't get any fog, it should be fine. Luckily, we don't get any of that here in this country. But I think, again, it's a first step in actually being able to build this solution kind of on a more long-distance way. And actually, the beauty of it is because the way this is encrypted, it doesn't really matter whose satellite it is, because they're never able to do anything with the key or with the source. Use cases, I think these are probably obvious. They're using this in a human genome project in Japan. Distributed data centers. Perhaps there's a failure somewhere. You need to use the internet. Or you need to use something that's not as trusted. You could use it there. All the other usual stuff that we get: power grids, telecom networks, and then satellite, particularly in remote areas. Or in kind of emergency situations or military situations. This is a way of really securing data anywhere you go. This is something we've actually trialed with a customer, not Equifax obviously, but actually a lot of we have a big finance community of customers and BTGS, Global Business and Finance, and there's a lot of interest in this. So we've done a few trials with them, and customers, the feedback on this is really positive, but it's still not, we've still got a bit more work to do to make it productionized, which I'll come on to. We also did a trial. This is more working with some other manufacturing equipment makers, not people doing manufacturing, but again, we've seen attacks on automated factories. I always think of Terminator, which is running when I think of this, where the factory starts coming alive, but people hack a factory, start turning machinery off. I'm always worried that someone kind of hacks my nest and turns my boiler to high, and I come home and my house is burned down. But the kind of risks of automation in that way this could be a way of securing the control plane for a factory like this, such that you don't need to worry about random Joes starting to build stuff when you're not expecting it. So we actually found this, a way of actually productionizing this was actually to use virtualization. So, and we all know what NFV was, so I'll kind of skip over that. But if you imagine, we can take all the key management out and all the optical controller and packet controllers, take all them out, use that in a central orchestrator that can do can do things like, oh, we've detected that someone's snooping, and then change the keys and kind of automate the whole thing, and deploy virtualization at different places, such that this would be a much more deployable service, and then use that to use the virtualization to do the encryption as well, potentially. There's still some issues with that because the virtualization really doesn't cope well with that kind of load. But in theory, you could use this as a way of, use SDN and NFV as a way of building the solution in a way that scales for customers. So, and we've done this, so we used this. So one of the things that we often get from media companies is, why was my episode of Game of Thrones on the internet before it was on the TV? This could be a way of transmitting that to the remote sites where you know that the content got there, you know it was delivered securely, you know that no one could have hacked it or intercepted it, and actually when Game of Thrones comes out, it's a new episode for everybody. And that's a real use case, and we're talking to a couple of broadcasters about that as a trial, and we're using it with some of our own content in BT Sport. I'll skip over this because I'm running out of time. We work with Bristol University on this, who are real experts in that, and we've submitted a few papers to OC and other places. I'll skip over that. So this is kind of leading up to how we built the kind of virtualization platform with key servers and QKD servers, and effectively put this into a kind of Etsy NFV platform with Mano, and allowed us to actually build the service on demand. This is some of the detail of the workflow in terms of create a VNF, get the key, encrypt it, and make sure that everything in the NFV as well as anything that you're transmitting is delivered in a secure way. And then working with Cambridge, earlier this year we built a real platform between our Astral Park site and Cambridge University at the Science Park, and this is running and it works, and we're using it as a kind of a way to generate new use cases and test new ways of doing this, and a way to make this technology simpler and simpler. And then we want to take that and deploy it probably somewhere in London for a 500 gig link, and we're working on that right now. There are some challenges with clocks in particular. We use GPS quite a lot on the network today, which works for network synchronization, but for this type of quantum clock synchronization, you need something a bit more. But our use case is to do some sort of credit card thing. We'll kind of generate a whole bunch of fake credit card numbers and see if anyone can attack them. And we're thinking about doing what do they call those things? A hackathon on it, to see if anyone can get into it. We're pretty confident about it, though. It's just more on the topology. I'll skip that. More detail on the systems. The slides are on the web page if you want to have a look at it and go into the depth of it. But it kind of talks about the trusted modes and the way that this works from a logical point of view. And I'm out of time, so I will stop at that point in time. We've got much more going on the roadmap, trying to get some momentum with the European Space Agency to see if we can do a more real trial with some satellite technology. So in a nutshell, encryption has its usefulness is probably limited. We need something else. We also need to be able to detect when something bad's happened, and this is a technology and probably a plethora of technologies that we will need to drive that secure network in the future. And that's it from me. Thank you very much.
Thank you, Neil. Any questions for Neil? Charlie?
Thanks. Charlie from Comsworld. Do you think that this encryption on the wire, layer 1 encryption sort of thing, will provide a solution to the slightly grubby SD-WAN kind of approaches that we're having to do? As a service provider, it'd be nice to be able to say our entire network is, you know, encrypted at layer 1, and we don't have to VPN full mesh all over everything to give anyone any security. You know, obviously, if you want full control, you would VPN yourself. But as a service provider, do you think that helps you?
I would say no, because the challenge there is as an industry, we've really decided to have lots of virtual networks on infrastructure, and I think, you know, the control plane for those two things are different, and I think if you try and mix them, you just create vectors of opportunity for the bad guys. So in my mind, I think, yeah, we need to secure every layer of the network, and we need to do that in a way that one doesn't expose a weakness in the other, which is actually where, if you look at pretty much every attack or every hack that happens, quite a lot of them are where those two layers didn't intersect correctly. So I would say probably doesn't help us, but I'd also, you know, I think there are. I think in the SD-WAN example, in my mind, I think how we identify what traffic and classify it is something that, you know, we've kind of resisted for a variety of good reasons. I think the more we see people taking that approach, the more, you know, no one cares about their Facebook traffic, whatever, but I do care about the traffic to my bank that's, you know, where I'm doing merchant transactions. I think we need to figure out better ways of signaling what that traffic is, so that we can wrap that individual traffic in the right security levels. I think we've kind of, and I kind of feel guilty about this, we've kind of chickened out of trying to do that. Again, some for very good kind of privacy and security, and you know, we just want to carry the packets reasons. But I think that those days, in my mind, I think those days are behind us.
Hi, it's Simon from Bogons. Neil, you say that one of the good things is that you can detect people trying to tap the fibre and things like that. That's great in the lab, but in the real world, we see that just people working in a splice joint or something like that can add a little bit of loss or something that comes and goes. How do you sort of differentiate between good and bad changes?
Those things are, so how you differentiate between those, every kind of thing that you do there is predictable. And you can, you know, I can tell, you pretty much tell when it's someone's fiddling with a splice or they've put a kink in the fibre. It's actually quite predictable. And actually, we have this running on real fibre between at Astral Park in Cambridge, and we can still detect it. And we can detect when people are, you know, actually we can detect there's a train line near it. We can actually see when the train goes past, because it does some stuff with the phase. So all of those things are detectable. They're patterns. You need to learn them. You need to learn those patterns and then use the pattern to say, okay, this is someone fiddling with the fibre versus this is someone hacking it. When someone puts a tap in, it's very noticeable. So if you, I mean, and you could do this in an experiment. Get a couple of optical testers, put a tap in, and just see the readings. I mean, it's that, you know, it's that obvious that someone's done something. You know, and this kind of just builds on that kind of capability, but builds it on a way that we can signal it and say, you know, set the sirens on because we think someone's genuinely trying to attack, because what they'll be looking for in the key will signal, you know, it would immediately, if they knew we were using a kind of key technology like this, they're going to try and attack the key, we would know right away that this was someone attacking the key because of the pattern we would see.
Okay, thanks.
No more questions. Thank you very much.